Hi, today we are going to see RFM system design concepts. At first, we will look at active RF components. The components that are used for low frequency operations are no longer useful in radio frequencies. At high frequency modes of operation, additional capacitive and inductive effects enter the solid state devices and change their performance. By analyzing the PN junction and Schottky diodes, it gives the foundations of rectifier, amplifiers, etc. The implementations of bipolar and field effect transistors is more complex than of PN junctions and Schottky diodes. So, the physical properties of semiconductors is the operations of semiconductor devices dependent only on the physical behavior of semiconductor. Three most commonly used semiconductors are silicon, germanium and gallium arsenide. Each silicon atom shares its 4 valence electron with 4 neighboring atoms forming 4 covalent bonds. So here is the energy band level of semiconductors. In the absence of thermal energy, that is when the temperature is equal to 0 degree, all electrons are bonded to the corresponding atoms and semiconductor is not conductive. When the temperature increases, some of the electrons obtain sufficient energy to break up the covalent bond and cross the energy gap at a room temperature of 300 Kelvin. The band gap energy is equal to 1.12 electron volts for Si. For germanium, 0.62 electron volts. For gallium arsenide, 1.42 electron volts. These free electrons forms negative charge carriers that allow electric current conductions. The concentration of conduction electrons, semiconductor is denoted as N. When the electron breaks the covalent bond, it leaves behind a positively charged vacancies which can be occupied by another free electron. These types of vacancies are called holes and their concentrations is denoted by P. In thermal equilibrium, we have equal number of recombinations and generations of holes and electrons. So here, this is valence band, that is a lower level where the electrons goes from lower level to the higher level. Energy is transferred from lower level to higher level. Where electron band, we have electrons here, it will be transferred from here to the conduction band. So that is called as an energy band levels. So we can write in a formula called, for n type of semiconductors, we will write n c e power minus omega c minus omega f divided by kt. Kt is a Boltzmann constant. P equal to nv e power minus wf minus wv divided by kt, where ncv is equal to 2 into 2 m p state and n state pi kt divided by h square whole power 3 by 2. The major part of RF system deals with Schottky diodes and PN junction diodes. So today we are going to see about PN junction diodes. So the physical contact of P-type with N-type semiconductor leads to one of the most important concepts when dealing with active semiconductor devices. The difference in the carrier concentration between two types of semiconductors. A current flow will be initiated across the interface. The current is known as diffusion current and is compressed of electrons and holes. So the PN junction diode, we have a P-type and N-type. When it is forward bias or reverse bias, there is a diffusion takes place here. So we will go for forward bias and reverse bias. So when a negative is applied to P-type and positive is applied to N-type, it is called as reverse bias, and whereas positive is applied to P-type and negative is applied to N-type, it is called as a forward bias. So during this forward bias and reverse bias, the space charge between the PN junction is comparatively it is different when compared to electric field distribution in PN junction, whereas reverse bias we have more electric field, but whereas in forward bias we have very less electric field. So the voltage distribution in PN junction, when compared to forward bias, reverse biases, we have more voltage distributions when compared to forward bias. So next we move on to Schottky Diode. So this is a symbol of Schottky Diode, where one side is attached with metal and another side is attached with N-type silicon. So there is only one junction which is having positive or negative. It is very small. So when a p-type semiconductor is joined with a metal, electrons diffuses into a metal and leaving increased concentration of holes in a semiconductor. The valence band bends towards the Fermi level because of higher concentration of holes, and conduction bands which bends away from Fermi level because of lower concentration of electrons. For both forward bias and reverse bias, this Schottky configuration offers low resistance and current flow in both the biases. When N-type semiconductor is joined with a metal, a positive volume charge density is created due to electrons migration from semiconductors. So here is the energy band diagram of Schottky diode. So this is valence band, this is conduction band, where energy goes from here to here. So we have a VI characteristics of Schottky diode. So that is, electrons diffuses from N-type semiconductor and leave behind positive space charges. The depletion layer increases until the repulsivity of the space charge stops the further electron diffusion. So the work function is measured from Fermi level to the reference level, where electron becomes free particle. So in previous sections we seen about PN junctions and Schottky diode. So now we have bipolar junction transistor, that is called as BJT. What is a transistor? A non-linear three-terminal active semiconductor devices where the flow of electrical current between two of the terminals is controlled by third terminal. The name is an acronym for transfer resistors. Transistors may be used in circuits such as amplifiers, oscillators, detectors, switches, and etc. It has three layers of semiconductor and two junctions. The semiconductor layer may be alternate N-type and P-type or vice versa. So BJT, we have two types of transistors. One is NPN, another one is PNP. So NPN, for NPN transistor, P act as a base, where PNP transistors, N act as a base. So we have a configurations of EB, C, CB. Okay. So these are the symbols of NPN and PNP. So we have a conceptual circuits of transistors and BJT DC biasing. So here, to obtain a single transistor characteristics curve that is plotted for characteristics of BJT IC and VC plane with IB as a parameter, DC volt source is set to a voltage, and then VCE voltage source setting is theoretically varied from 0 to infinity while measuring corresponding collector current. So here is the characteristic curve for a character BJT. So this is a cutoff region, so and it starts from here, so we'll say this is a cutoff region, and this is a saturation region. So we have a number of values 1, 2, 3, 4, 5. So these are the characteristics of BJT DC. So the DC biasing of a transistor plays a major role in the operation and proper functions of an active circuit. So it is a setting of DC voltage at each of the two transistor junctions of EBJ and CBJ, such that the transistors will perform in stable fashion in Indian mode. Proper values of each two transistor junctions voltage can be translated equivalently into terminal current values such as emitter or collector, which can alternatively be used to specify DC bias values of the transistor. The currents in the co-junction with the bias voltage values of junctions make the DC bias specification of a transistors to make it DC biasing complete. So next we move on to BJT modes of operation. So in this BJT modes of operations, so we have 4 modes operating. One is inverse mode, second one is cutoff mode, third one is saturation mode, and fourth one is active mode. So in this saturation mode, in which EBJ emitter base junction and the collector base junctions are forward bias. In this mode, an increase in base current produces no further increase in collector current. So cutoff mode, in which both emitter base and collector base are reverse bias, thus there is no current for any current through the circuit. IE is equal to 0, IC is equal to 0, and IB is equal to 0. Active mode is where emitter base is in forward and collector base in reverse. This mode, the collector current is proportional to the base current. So IC equal to beta IB, where beta equal to CE current gain, collector emitter current gain. IE is equal to IB plus IC, where IB equal to 1 by beta into IC. IC equal to beta divided by 1 plus beta into IE, that is equal to D into IE, where alpha equal to beta divided by 1 plus beta gives common base current gain. After the first order model for the operations of transistor in active mode can be represented by hybrid pi equivalent circuit. IC equal to IS E power VB divided by VT. IS is reverse saturation current, VT is thermal voltage, where VT equal to KT divided by Q, that is a Boltzmann constant of 1 point, K equal to 1.38 into 10 to the power of minus 23 joules per Kelvin. So the first order model of active mode, the forward bias causes an exponentially related collector current. So here is the two possible large signal equivalent circuit models of NP and BJT in active mode. So in this, the collector terminal behaves as a non-linear voltage controlled current source depending upon exponentially on VBE. So beta is a common emitter current gain and is much larger than unity for good transistors, where beta is double greater than or equal to 1. As a result, IB is seen to be much smaller than IC. Furthermore, because alpha is very close to unity for a good transistor, the collector current IC is approximately equal to emitter current. The inverse mode is a mode in which emitter base junction is a reverse bias and common base junction is in forward bias. That is, emitters and collectors roles are reversed. This mode may theoretically be used in the same manner as active mode. So that's why we have two possible low signal equivalent circuit models of NP and BJT in active mode. So the next topic is radio frequency field effect transistors. So what is field effect transistor? It is a monopolar device. It carries only one type, either holes or electrons, that contributes to the current flow through the channel. If the hole contributions are involved, so P channel, otherwise or N channel FETs. FET is a voltage control device. A variable electric field controls the current flow from source to drain by changing the applied voltage on the gate electrode. So we have four types of FETs. One is MISFET, that is called metal insulator semiconductor FET. Second one is JFET, junction field effect transistor. Third one is MESFET, metal semiconductor FET. Next one is HFET, that is called as an hetero field effect transistors. So next we move on to constriction functionality of field effect transistors. So it is importance in RF and microwave amplifiers such as mixers, oscillator circuits. So we focus analysis on MESFET, whose physical behavior is many ways similar to JFET. The analysis is based on geometric, where the transistor is operated in a depletion mode. So we have the operation, one is in linear region and the operation another one is in saturation region. So as the drain source voltage increases, the space change domain near the drain contact increases as well. resulting in a non-uniform distribution of the deflection region along the channel. If we assume that the voltage along the channel changes from 0 at the source location to VDS at the drain, then we can compute the drain current from non-uniform space charged region. This approach is also known as gradual channel approximation. The approximation rests primarily on the assumption that the cross-sectional area at a particular location along the channel. So here we have P, that is called as a depletion region. So this makes which is positive and which is negative. So this is a linear region where we don't have the drain, but whereas in the saturation region we have a number of voltage drops. So the next topic is high electron mobility transistors, that is called as HEMT. So this is the generic heterostructures of a depletion mode HEMT. And thus GaAs, gallium, this is gallium, this is aluminum, this is arsenide. So we will call it as aluminum gallium arsenide. In this we are using gallium arsenide and as well as aluminum gallium arsenides. So what is high electron mobility transistors? It is also known as modulation doped field effect transistors. Exploits the difference in a band gap energy between the semiconductor materials such as aluminum gallium arsenide and gallium arsenide in effect substantially. So that is, we will maintain for a MOSFET we can go with a low noise performance and high power rating. Transition frequencies of 100 GHz can be achieved due to this HEMT. The high frequency behavior is due to separations of carrier electrons from their donor sites at the interface between doped aluminum gallium arsenides and undoped gallium arsenide layers, where they are conformed to a very narrow layer in which motion is possible only on the parallel interfaces. Here we have two-dimensional electron gases. So this is called 2DEG, that is called as two-dimensional electron gases or plasma of very high mobility up to 9000 centimeter square voltage per second. So aluminum gallium arsenide as n-doped semiconductor is followed by an undoped gallium arsenide space layers and a high resistive semi-insulating GA gallium arsenide substrates. The two-dimensional electron gases forms n-doped layer in GaAs at a zero gate bias condition because the Fermi level is above the conduction band. So it is above the conduction band. So the electrons accumulate in this narrow potential. The electron concentration can be depleted by applying increasing of negative voltages to the gate. HEMT are primarily constructed for heterostructures with matching lattice constants to avoid mechanical tensions between layers. So here are some examples. A larger in gallium arsenide lattice is compressed into smaller gallium arsenide lattice. Such a device configuration is known as pseudomorphic HEMT or PHMT HEMT. The next topic was basic concepts of RF designs. So RF circuit design considerations have to go through 3 steps of design process. First one is the design process starts with selecting a suitable device and performing a DC design to obtain a proper point, where the step 2 deals with the device which can be characterized to obtain its AC small signal parameters based on specific DC operating point selected earlier. The circuit matching concepts is having stability consideration, gain consideration and noise consideration, where these 3 will have a very good output when comparing to others. So it consists of designing two matching circuits that transition device to outside the world, the signal source at one end and the load at another end. So we have some facts connected with the design process. That is, the length of the circuit is generally much smaller than the wavelength. That is L double smaller or equal to lambda. This is condition number 1, and the condition number 2 is propagation time delay, where Td is equal to 0. So the third one is we have low frequencies, time delay, and lumped circuits can be used. So now we are going to see a topic on mixers. So what is a mixer? A non-linear 3-port circuit which have 2 inputs and 1 output. So this is the symbols of mixer. The spectrum of output frequencies is equal to the sum of difference of 2 inputs frequencies and their harmonics. So where RF is radio frequency, where IF is intermediate frequency, and the last one is local oscillator. So we have a block diagram of mixers where the mixer uses the non-linearity of a devices to generate a spectrum of frequencies based on sum and differences of harmonics of RF signals and local oscillator signal frequencies. Actually, this local oscillator will produce a signal to mix with RF source and give it an intermediate frequencies. So the nonlinear device is a flank on 3 sides by 3 matching circuits which need to be designed properly for maximum conversation efficiencies. So in general, the mixer utilizes one or more nonlinear devices properly pumped with effective large signals. So like as in local oscillator. So to mix with RF signals in order to generate a spectrum of frequencies based on sum and differences of harmonics to make a frequencies. So in this block diagram we are creating a simple input. So it is a RF source. This is a transmission line. It is passing over through the load. So losses of matching circuit. So if the input is given to it, the matching circuit will match the input whether it has equal sources or not. If there is no, it will replicate it, and if it is correct, it will pass to the 3-port network or a device. So it will, where the local oscillator will mixes over here, the radio frequency is changed to an intermediate frequency where the losses and matching circuits will go on, and it will be given to the load. So we have 3 types of mixers. One is up converter mixer, second one is down converter mixer, and third one is harmonic mixer. So let me look at harmonic mixers. A simple method of down converting a high frequency RF signals when only a low frequency exists. The use of harmonic mixers. Frequency down conversions is achieved by mixing the high frequency signal with an appropriate harmonic of low frequencies, where Wi equal to n omega naught minus omega, where n equal to 1 to up to infinity it is an integer, where n equal to a fundamental down converter is. When n is 1, it is a fundamental down converter is obtained. The applications for harmonic mixers are in millimeter wave instrumentations, where use of high frequency sources which can generate substantial power to satisfy low power needs to be impractical of very expensive. Next, we are ready to see the up converter. So here is the block diagram for up converter. In this we have a mixer. So intermediate frequency, higher frequency. So up converter uses intermediate frequency into radio frequencies, whereas down converter uses radio frequency into intermediate frequencies. So we will see a counter. When a mixer is used as an up converter, the sum of frequencies of F out, which is equal to F in is F R. So it is utilized and differences of frequency is rejected. The intermediate frequency oscillator is modulated with desired information signal, which when mixed with low signal to generate the desired frequency conversion. Use of mixer as an up converter, particularly in case of radar or transistor work, is an advantageous because it allows use of single local oscillator for both receiver and transmitter. The use of proper filtering or an image rejection mixer is needed to generate the sum of frequencies of omega r equal to omega naught plus omega I, that is output simple. So an up converter is used in a transmitter to modulate a carrier wave with an information bearing signal in order to generate radio frequency signal for a transmission. Next we move on to the down converter. So in this down converter we will go with radio frequency to intermediate frequencies. So this down converter requires the different frequencies. So last we'll say that F naught equal to Fi plus Fr, whereas F naught equal to Fi minus Fr to sum of the filtered out. The use of mixers as a down converter in heterodyne receivers have several advantages. The intermediate signal being in the range of 10 MHz less than or equal to 100 MHz lends itself for low noise amplification because intermediate frequency noises is more than IF when compared to RF frequency range. By changing the low frequency, a heterodyne receiver can be tuned to receive a wide band of radio frequencies without a need of high gain wideband RF amplifier. So a down converter is a mixer. It is used to shift the low frequency of an RF signal substantially down to an intermediate signal ready for a further signal processing. So the IF signal frequencies is given by WR equal to WI equal to WR minus W0, which is in magnitude. Such mixer is used in receiver as a demodulator to remove the carrier wave from the transmitted signal in order to attain the information carrying signal. So next we are going to see low noise amplifiers. It is an electronic amplifier that amplifies very low power signal without significantly degrading its signal to noise ratio. Low noise amplifiers are designed to amplify a signal while minimizing additional noises. It is found in radio communication systems, medical instrumentations and electronic testing equipment. So here is a block diagram of low noise amplifier. We have an antenna, so duplexer, low noise amplifier and power amplifier and RF system. So for this RF system, how the low noise amplifier is going to work? A typical low noise amplifier may supply a power gain of 100 while decreasing the signal to noise ratio by less than factor of 2. The low noise amplifier of a receiver path and power amplifier of transmitter path connected to the antenna via duplexer, which separates the two signal and prevents relatively powerful power amplifier output from overloading the sensitive low noise amplifier input. The primary parameters of noise figures gain and non-linearity for low noise amplifiers. So the noise is due to the thermal and other sources with typical noise figure of 0.5 to 1.5 dB range. So So the noise figure helps determine the frequencies of particular low noise amplifiers. So low noise amplifier figures in results for better signal receptions, where low noise figure must have a high gain. Typical gain is between 10 to 20 dB for a single stage. So we have a number of applications for low noise amplifier. It is used in industrial scientifics and medical bands, radios, cellular telephones, GPS receivers, mobile phones, wireless LANs, and satellite communications. So next one is voltage control oscillator, we call as VCO. So here is a block diagram of VCO: input voltage and voltage control oscillators, and an output voltage which is proportional to output which is proportional to Vin. So it is an oscillator with an output signal whose output can be varied over a range, which is controlled by input DC voltage. So the output frequency is directly related to the voltage and it inputs. The oscillation frequency varies from few hertz to 100 hertz of gigahertz. So we have types of voltage oscillators also. One is harmonic oscillators, second one is crystal oscillators, and tank oscillators. So next we are going for basic working principles of sawtooth wave generator of voltage control oscillator. So we have input from controlled voltage source and constant current source, and we have an amplifier and also reference voltage. So we have a BJT where NPN or PNP took place, and there is capacitor that is grounded to it. So the output signal with a sawtooth or triangular waveform provides a wide range of operation frequencies. The output frequency depends on time of charging and discharging of capacitors. So for a voltage control oscillators, generating a sawtooth waveform, main component is a capacitor whose charging and discharging actually decides formations of output voltage. The input is given in the form of voltage which can be controlled. This voltage is converted into a current signal and is applied to the capacitor. As current passes through the capacitor, it starts charging and the voltage starts building across it. As the capacitor charges and the voltage across it increasing gradually. The voltage is compared with the reference voltage using a comparator. When capacitor voltage exceeds the reference voltage, the comparator generates high logic output, which triggers the transistor and capacitor, which is connected to the ground, and it starts discharging. Thus, the output waveform generator is representations of charging and discharging of a capacitor. The frequency is controlled by input DC voltage. So we have applications of voltage control oscillators also. So this voltage control oscillators is used at jamming equipments, phase locked loop, communication circuits, function generators, and frequency synthesizers. So the next topic is power amplifier. So in radio frequencies we need a much more power amplifiers. So power amplifier is the last component of transmitter chain. The purpose of the transmitter is to deliver an RF signal with required properties and the specific power levels to the antenna, and need for power amplifier is an amplification of signal, that is the antenna need to transmit from one place to another. So the requirements of power amplifiers are sufficient gains, power handling capability need to be high, and it is always need to be stable. So when comparing with power amplifiers, we have power amplifier relations also. We have generic power amplifier systems with the RF source and input matching network and matrix source and output matching network, and load is also given, and input is given to it, so it will amplify and it will give it to the load. So the input and output matching networks are need to reduce undesired reflections and thus to improve the power flow capabilities. The amplifier is characterized through its S parameter matrix at a particular DC bias points. So in this power amplifier relations, gain and noise figure, gain must be high and noise figure must be low. The output power is also in dB, which must not exceed 10 dB. So the transducer power gain, it quantifies the signal gain of the amplifier placed between the source and load. So the formula for transducer power gain is GT is equal to PL divided by PA, power delivered to the load by available power from the source. So the next topic is stability considerations. In the stability considerations, an amplifier circuit must be stable over the entire frequency range. RF circuits tend to oscillate depending on operating frequencies and termination. The phenomena of oscillations can be understood in the content of voltage wave along the transmission line. If the transmission line is greater than 1, then the voltage increases, that is magnitude, possibly causing instability. Where the transmission line is less than 1, causes a diminished return voltage.